Hello, it's me again, Jean-Louis Van Bella, and this time it's really me, not AI or some mix of ChatGPT and me. It's really me. I want to follow up on my last video, Physics and Cosmogenesis, which presented like a 20-minute talk, a dialogue between ChatGPT and then myself, but restructured in sort of mutual contributions to the discussion. We discussed the conceptual challenges really in what I would call the standard model, especially the assumption of a strong force or a nuclear force, and the various contradictions that this yields, especially the classical conservation law of energy and yeah, the fact that you model really weird new forces, while the only force we know is the electromagnetic force. So here I want to go much deeper. It's probably a combination of promoting my papers and then really showing you how I work with ChatGPT as a very advanced intelligent system to try to build models that confirm or don't confirm what my wild theories are. So this video is going to dive into another, I would say, experimental exploration with what GPT, what these large language models with the mathematical problem solvers that attached to them can do. It's going to focus on the crux of what I talked about yesterday. Models in which you have multiple moving charges exerting, force on each other. How can you model that? And I bring it down to modeling what I call the deuteron nucleus problem. So to present the background of that, I'm gonna briefly show you the principal papers I wrote about that. One is De Bruij's matter wave, the concept and the issues, where as you can see it has a lot of reads, and it ties in with a broader non-mainstream interpretation of quantum mechanics that is not the Bohr-Heisenberg interpretation. It's an interpretation rooted in Schrödinger's own views on his wave equation that it should model real orbitals of charges. Schrödinger's equation models one electron orbiting around a very massive central positive charge, the proton. It's a hydrogen electron orbital model. But based on that, this assumption that it models something real, as you can see among the list here of contributors or members of this Zitterbewegung Institute, with David Hestenes, who's in the 1990s, sort of single-handedly revived a more classical or realist interpretation of quantum mechanics, I would say. It's not non-mainstream anymore, I would say. I would like to highlight here Oliver Conce's website, a brilliant, much younger man. He was an academic physicist. He's active in the ICT industry as well. He's done a lot to sort of open discussions on public forums and bring this sort of non-mainstream, classical, realist, simple interpretation of what quantum physics really is about into the attention of the public and academics. I think this should be Andras. I googled on Zitterbewegung. That's probably Andras Kovacs, a brilliant man. Also a young researcher in the private sector, and you can see this is really making waves, I would say. But so the topic here is that in my video yesterday, I said, well, we need to move beyond a single charge, modeling an electron, modeling a proton as a blob of charge, probably It's where I differ a bit from Zitterbewegung models in my modeling of a proton. We need to develop a deuteron model, all right? A proton and one neutron, what makes them stick together? And that's sort of where I go about, these multi-charged Zitterbewegung models. It's an incredibly tough problem because building on the idea that a neutron itself. So what we have, let me recap the discussion. In hydrogen, we have one proton, right? It can exist on its own. We have a one proton nucleus. We have the hydrogen 2 isotope, which also shows that proton and neutron can combine in a very stable combination and form a nucleus. How is that? Why would a neutral particle stick so close and the neutron stick so closely together with a proton? The hypothesis here is that not quarks and gluons and stuff, but very simple is that the nucleus of deuterium, deuteron is the nucleus of deuterium. One proton, one neutron would be a dynamic combination of a positive charge, two positive charges, one of the proton and one of the neutron. Modeling the neutron really as a dynamic combination itself of a positive and negative charge. So beyond modeling electrons and protons, which I think we've done pretty well, these models are statistically deterministic, I would say, are stable situations modeled by basically the Planck-Einstein relationship. How do you model a neutron? How do you see these bands of a positive and a negative charge inside of a neutron? What are the dynamics? Why do they stick together? It's a bit of an extension of Feynman's model of an atom, a hydrogen atom. The Planck-Einstein relationship tells us the positive and negative charge won't just sit on top of each other, because that means no energy, no motion. Energy is a force over a distance, so it's motion. So if there's no motion, if we just have a positive and a negative charge sitting statically on top of each other, you have no energy, you have no particle, basically. That reminds me that it might solve the conceptual issues involved in matter antimatter annihilation, but it's another thing. That's something for a different lecture. But it's nice to talk about this because you see it inspires new ideas. But so the proton and neutron can stick together. So that would be a dance, or I would say like a three-body problem. You have a positive charge, two positive charges, spinning around or interacting, I would say, with a negative charge. Not interacting in the sense of an electron orbiting around a massive center, positively charged center, like the hydrogen atom, but no, the three charges dynamically spinning around each other. And then you can argue probably it's a dynamic equilibrium between which charge has the most energy, kinetic energy at some point in time, where the potential energy goes in the electromagnetic dipole field that is generated by the motion of the charges. So it's like this perpetuum model, but applied to two charges or three charges in a deuteron. We can then go to the helium atom. The helium atom, there's two isotopes. The most prevalent is two protons, two neutrons. So that means two positive charges and two neutrons. So that's that's six charges. But you also have helium-3, which is just two protons and one neutron. So that you have a four-charge model. And that's what I write about here in this paper. When Zitterbewegung theory is very nice and wonderful and beautiful, but how do you go about multi-charge Zitterbewegung models? There's very little modeling around that. Well, I wouldn't say that. I pulled this up. I was actually looking for Andrew Meulenberg, but I didn't quite find it, who does a lot of research on these what he calls deep electrons. So that's the negative charge in a neutron, deep electron orbitals. And as you can see, this is just, I randomly pulled it up, Noriyuki Kodama, there's really a revival of old nucleus models of the 1920s, which indeed model neutrons as a positive and negative charge and say, well, it's the neutron really that acts as a glue in a nucleus, not the quarks or gluons. And if I say the neutron, well, the neutron has a very dynamic combination of positive and negative charge. And then you have the Platzwechsel model of Schrödinger that comes into play, where a neutron and a proton in the dynamic combination that they form inside of a nucleus. Platzwechsel means proton becomes a neutron becomes a proton, they exchange charge. It becomes very, very complicated, and I'm going to be talking for hours if I continue on this topic. So let me go back to the script that ChatGPT generated for me to sort of stick to a script. So theoretical framework is fairly easy. I really want to, build a modern theory, but it's actually, going back to classical physics, assuming there's only one force, the electromagnetic force, which is, quite complicated. In its structure, it's a right-handed force or left-handed force, depending on your conventions, two components, relativistic effects come into play. But it's a force that is well understood, and it's conservative force, which is very nice, because if you have non-conservative forces like this, nuclear force derived from a Yukawa potential or weak interaction, you arrive at very strange things. So what are the challenges really in modeling these multi-charge dynamics? Now I'm going to turn a little bit to my chat. It's a chat I can't share again because I uploaded a lot of my papers in a raw format, a Word format. Where is it here? Chaos theory. Yes, here it is. It's pulling it up again. I agreed with it that I would share this chat by scrolling over it. We generated it fairly quickly in just an hour. I basically started with just checking, and that's an important thing if you want to work with ChatGPT as an amateur researcher like me, or as a PhD student. Is I feel when you're working on these models and you use the power, the computational power, and also sort of the reasoning power of ChatGPT, you need to agree on what Mr. Wong in his CES 2025 speech called foundational model, sort of a common shared vision in which ChatGPT does not only execute instructions, but really understands what you're talking about. So I started with a general question on indeed, if we start modeling equilibrium, disequilibrium states, statistical deterministically models, systems of equations where you don't know the initial conditions. To put it simply, like if you don't know where exactly you are in this cycle, then you can't predict where you're going to be in the next cycle in so many time units from now. So I asked it to sort of check a little bit on how deep it understands that kind of stuff. And so I said, look, Feynman once wrote this, the tiniest irregularities are magnified, so we get complete randomness. I don't find that a very precise scientific term, or what is randomness. But yeah, given an arbitrary accuracy, no matter how precise, you can find a time long enough that we cannot make predictions valid for that longer time. It's not millions of years like in cosmogenetic models. No, at smallest of scale, the accuracy needs to be 1 part in a billion to get anything, and even then the time goes logarithmically with the error, and in a very, very tiny time we lose all our information. And I said, that's a bit obscure. Can you ground it in where does this come from? Feynman's remark, and it did really great job in terms of immediately delving into chaos theory, statistical mechanics, dynamical systems. So that was sort of on entropy, stochastic processes, nonlinear dynamics, and that sort of reassured me that I could move to the hard questions that I can't solve. So I asked it then, okay, this is very nice. It explains Feynman, and you really understand what statistically deterministic systems are. So let's apply it then to one particle, these perpetuum mobile models that I've built of electrons and protons. But let's work towards a system of equations. An electron and a proton, basically, really it's easy formulas, tangential velocities, orbital frequencies, and the Planck-Einstein relationship, which basically says that a dynamic system like that will have an energy that is equal to 1 unit of Planck's quantum of action. So, but here I ask it sort of, well, it suggested itself. Let's do these differential equations. Came up with Lorentz systems. Yeah, how sort of these mathematically or statistically deterministic systems can become chaotic, and how sort of equilibrium situations can be a knife edge, which is what they probably are. I mean, Schrödinger's wave equation for electron orbitals. Feynman writes about that. Why is it so precise? Well, that's the big mystery of nature. I said an electron and a proton will pack exactly 1 unit of Planck's quantum of action, and nothing more, nothing less. And it's sort of these, the equilibrium that you have with a superconducting loop. So he generated a lot of stuff, asked about phases, and the concept of strange attractors. The conditions under which a inherently chaotic system does converge to these exact patterns of motion, I would say, that incorporate Planck's quantum of action in one or a multiple of it. So I did really great on that. But then we zoomed in. Let me scroll down on. I asked it to develop a few other things. It really showcases. I learned more about chaos theory and strange attractors than I could ever have in just 5 or 10 minutes than all of my reading on it in the past. Nice trajectories, and then I went into plasma physics. So sort of to test it and then move to indeed these multi-charge Zitterbewegung models. Said, okay, plasma physics. Let's talk about that. If we have like a number of protons that we keep together in a confined space, we will only have the electromagnetic force. The proton might have a varying. That was interesting. It immediately understood what I would say. No, it's not a fixed magnetic moment, but if proton is a blob of charge, then we're talking time averages, and again there that creates it's very difficult to model, because the phase of all these protons is not necessarily aligned, and that leads to very difficult mathematics, where basically in plasma, if you want to control plasma, keep protons together in an accelerator or a storage ring, I would say. Tokamak says here, or is it Tokamak confinement strategies. It came up with these suggestions, and it said, yeah, that's how it works. A real world parallel to Tokamak confinement strategies. So I sort of I didn't skip over that. I let it generate, but here it becomes interesting. Then I sort of said, like, model like 10 protons and in a quadrupole field that keeps them together with magnetic moment fluctuations for these 10. I don't know if you did it, probably it used a static magnetic moment, but that's where I want to go on the limitations of ChatGPT as I use it. It does these simulations, but we never got out of what you see here, basically. Linear trajectories, in this case, protons being pushed together, or some of them escaping because of the repulsive force between them. I queried it. It admitted a bit that, it does simplify the situation by focusing on, let me see that here, basically not taking into account magnetic forces. Although it did here, but it said it might have not been strong enough. The magnetic field, but that's the quadrupole field. That's not the magnetic field that is generated by the motion of these protons. And I can go on and on and on. We changed cycle times, or let's say the time window over which the simulation runs. And it's I found that it says like, oh, okay, here you see non-linear trajectories, curvature, interaction that you would expect apparently from the simulation it does. The simulation is nice. It quickly generates. It uses Python to sort of model all that stuff. But yeah, it does use the Lorentz force I see here. So not only electrostatic but also magnetic effects. It does a great job. But I said like your visuals don't show what I want to see. Dynamic equilibria. Charges dancing around each other in circular or elliptical. They're equivalent in 3D space basically. Or Lisa drew like trajectories like that one that I have for my one charge proton model. It worked, and I let it reiterate and rewrite code. But the visuals weren't great. I mean, the visuals were what they are, but you clearly do not see some kind of dynamic equilibrium like in a double star system, two masses that rotate around each other, or what we indeed say, this the two-body, three-body problem that we have when you look at the deuteron. The deuteron nucleus, two positive charges, one negative charge, and somehow these need to dance around each other. The three-body problem is very notorious in physics, and there is no general analytical solution. But that's why I thought that ChatGPT could, apply this enormous computational powers to do numerical simulations. You see, it did its best at 50,000 steps. Several of the regenerations, I would say, of the images took 1 or 2 minutes. So I pushed it a couple of times. Then, as I go down here again, where I say, well, "What are you doing exactly? Do you understand what you're doing?" It said, "Yeah, I'm decomposing the deuteron. I do analyze it as consisting of two charges, positive charges, a proton and a positive component of the neutron." And it becomes a three-body problem. Maybe the problem is that I said the proton might be a blob of charge rather than a point-like charge. Newton's law, that's where I found out, hey, but here you're going back only to modeling electrostatic forces. It tried various integrations. It really tries to do what I asked it to do, sort of, generate a simulation of this glue, neutron acting as a glue, or the negative charge inside of a neutron acting as glue between the one or more protons that make up the nucleus It applied, the binding constraint where it said total energy, kinetic and electromagnetic has to be constant, um, relativistically, non-relativistically. It tried, and but here you still see that this is a figure where basically the two positive charges and the negative charges move away from each other, or maybe I don't know, I don't see the direction. Maybe the negative charge moves to the positive charges. In any case, these are all images of linear trajectories in an outside environment that is defined by we try to contain these things, but it's these are not stable trajectories. These so the energy dynamics that doesn't say very much, but it did calculate the images it generated and the equations it gave me are a bit of contradictory, I would say. What is it here? Yeah, that's quite a lot of code. You would say 100 lines is nothing, 120 lines is nothing. But it codes very smartly, and it digs into libraries, NumPy and other toolkits. Axis 3D, okay, that's for the graphics. I couldn't write that in such a short time, and I couldn't probably produce the quality it does. So that's the thing where I'm at, really, is how great it is. But at the end, it is what I said in the previous video. We I wrote it's I then said, okay, let's move to a different kind of math, and I uploaded my own papers, these ones here. Say go through the annexes. The annexes are indeed a very different approach to modeling equilibrium wave equations for matter particles in free space using. Is it gonna go there? No. Any case, that's my paper. It's one of my most downloaded ones where I show that Schrödinger's wave equation is perfect for modeling equilibrium situations that represent a real motion or real charge, in this case an electron around a massive static positive charge. I gave it interpretations of maybe we can go here, and I also told it like Schrödinger's equation is probably the one to use because it is relativistically correct, as I argue in this paper. That's a minority point of view, but go to this paper if you want to see it. This is 1/2 factor. It is often confused with the classical kinetic energy formula. Yeah, and X3 we are already here. So yeah, that's where I think ChatGPT admitted that that's a whole different kind of math. It analyzed, parsed it. It also found that that's interesting. I should rewrite. It says basically this is a great paper, great ideas, but I could probably do a better job at explaining why and how I do certain things. But it didn't really identify inconsistencies or errors in it. Just says, okay, you're not using symbols very consistently. Here it sort of went a little bit strange where I do dimensional analysis, and exactly that's the reason why I don't believe that the Yukawa force or nuclear force exists, because it doesn't have a unit. The Dirac or the Einstein or the Yukawa, you can't reduce it to SI units. That's one of the reasons why I think another force does not make sense. I located some other documents. That's why I can't share this chat. But I think that's really the future, actually, where I would encourage you guys, my listeners, hopefully young people, PhD students or just students of physics and math, to work with ChatGPT the way I do. Experiment with it. You use its power to quickly write Python code to build a model, and then run numerical simulations of it. Because I said the equations that you're going to inject into the model here, there's probably no way that you're going to find an analytical solution for them. But if you can generate numerical simulations, that would make sense. So I didn't manage to do that. I mean, this is my comment, and I'm sort of okay. I think I've exhausted my creativity. I'm trying to find Feynman's treatment of multi-particle models. He has one in which he uses coherent quantum math. I should look it up, but I remember that was like 15 years ago. The treatment was short and it was inconclusive. People won't like that. But yeah, you are attacking a very big problem in physics and in math here, to indeed do what I want to do here, a numerical framework. The analytical framework is there for simulating deuteron dynamics, but there's so many hypotheses you can use. Do we really want to model point-like charges? Or what about Schrödinger's Platz-Wechsel model? What is that deep electron inside of a neutron? I mean, its size, it must be very different. I could maybe pull up Desmos. I encourage you to play with that as well. Where are my graphs? Yeah, maybe you have a sort of a Lissajous trajectory combined, if this would be the positive and negative charge inside of a neutron. Is it something like this, or is it very, very differently? That's not easy. Let me see where I am. Probably I should wrap up. I'm at half an hour. That's not so bad. Where is ChatGPT again here? So yeah, let me finish scrolling through the various. That's interesting. Also, I'm not so much at home and post Runge-Kutta integration. There are others, Euler integrations, to solve coupled differential equations. But you can see it does advanced stuff. I mean, coupling differential equations and then specific solution methods for it. So it really works incredibly hard. Generating, regenerating code, inserting actually the actual codata values for the constants, the electronic charge, the mass proton, because I asked maybe that's the problem if you want to do simulations. Probably best to use codata values and then see where the points of stability or anchors are. Yeah, it didn't work. We get these linear trajectories, not what I have. If I can show, maybe in this one here, in my own model. It's not in here. Yeah, here I write about conservation law and why the nuclear force, this Yukawa potential, doesn't make much sense. Here I have sort of sublocal equilibria, but it's not what I was looking for. Maybe here. No, also not here, but in any case, the images I was looking at that I had inserted were like indeed simplistic, double stars, two masses orbiting around each other, and three-body problems being visualized, which you can find on Wikipedia. So that's gonna be it. Actually, I highlighted. Let me see if I did finish going over it and on conclusions if there were any. No, you can see we did a few iterations on it. It's simplified through Wig and the magnetic interactions. which I said, well, if you do that, you're surely not going to get anywhere. Um, and then I said, okay, let's just do a video of this and throw it into the open. I checked, it sort of says, please, to be consistent with ChatGPT, user policy, stress really that, this is not official, clearly separate out, what your ideas are, and just showcase how AI can assist in tackling your problems from concept to computation. That's what I like and what I wanted to illustrate here. ChatGPT thinks along. It takes a while, I find, but it really does what Mr. Wong, when he talked about his AI, the keynote speech at the Consumer Electronics Show a week ago, about which produced also a number of videos. He says how crucial it is, and really the next wave of AI to provide artificial intelligence with a physical grounding, a foundational model of reality, and that's what I found. That's what I did here. So I would say play with it yourself. We tried. We didn't capture sort of this dance between charges in a multi-charge model for the deuteron or for helium, helium 3 or helium 4. It is a work in progress, and I think the difficulty of the problem is what makes it exciting. So I would invite you to sort of do what I did. You can use my papers; they're open source. I can provide you with a Word document if you want. But you can just copy paste, throw it into ChatGPT and see what it thinks of it. That's nice, because it's also what I did. ChatGPT 1 or 2 years ago, I could not ask it to sort of say like, hey, this is a paper of mine. I'm not so sure about it. I think it's okay, but can you run like a sanity check on it? It does that perfectly well now. And that's where I wouldn't call it super intelligent, but I would call it, more intelligent than me in modeling physics and surely in solving mathematical problems. I think it's great in solving mathematical problems like this one, as I said in a previous video, because it really can sort of internally visualize, space and time, and better than we do, because it immediately sees relativistic effects, and it uses the relativistically correct equations of electromagnetic forces and motion. So that's all great. And so if you're interested in exploring these ideas further, I would say go on ResearchGate. It's open for all to read and build upon, and I said I asked ChatGPT to provide a script a bit. It ended with this optimistic note. I believe that together we can push the boundaries of what is possible in understanding the dynamics of the universe. That's hyperbolic language, probably quite typical for it. But I think it is a call to action. For me, I don't know. I hopefully will have less free time in the coming weeks or months. But if not, I will do that. Continue to push the boundaries of these models. So that will be it. I hope I did not ramble too much. If I did, sorry, then you will have probably switched off anyway. So I am at 40 minutes now, and that is great. And I will just upload this, and then we are done for the rest of the week. I wish you a great day and a great working week ahead.